Sir,
Yeah, Santhya.
the question they have given that has been 10. The vertices, number of vertices in the path should not be given. You have told no.
Yeah. That
It's
one
not
you could.
printed in the question.
That's right.
For that, if they give any grace mark like that, or what is the procedure for that? Generally, what they will do?
So generally, the thing I have observed in the past is that they give you, it'll be marked correct if you have
Oh,
attempted that question.
okay, sir.
Um, Whether you will be marked correct, whether you have not attempted that question or not, that is up to the discretion of the instructor.
Okay, sir.
So yeah. According to the solution, it looked like the 10 is missing from there. N is 10 is missing from there. So I pointed it out to Professor Palash Day, and
Okay, sir.
he told me to post it in the forum, and he has asked the NVDL people also to take care of it. So
Okay, sir.
yeah, soon probably they'll look into it, and the most likely course of action is that they'll give everyone full marks for that particular question. Okay.
Okay, sir. Okay, sir.
Yeah. But yeah, others also if yeah. But thanks for
Because
pointing out something. Yeah.
okay, sir. Because my internal mark is very low in, so that's why.
Oh, in the assignments.
Yes, in assignment marks. Because of that, only I'm asking. There is no in assignment marks. Best 8 they will consider for the internal mark, no sir.
Oh, okay.
I got only 60 marks. Before assignment also I got only 70, 80 like that only. So that only I have asked you.
Oh, okay. Okay. I mean that too is not too bad, and uh, but
But for my coursework, I have to at a external by combining internal and external mark, I have to get at least 85 percentage.
right.
Above 80, 75 percentage is the pass mark. For grading system, I have to get at least 80 to 85 percentage of mark. So
Oh,
that's
okay. And what is the weightage of the assignments as far as the total marks is concerned?
as per the total marks of systems, they will give other. I think so. Before, as per the wait, sir, so for assignment marks, 25 percentage of average from 8 assignments out of 12 assignments given as
Okay.
25 percentage of marks, sir.
25%. Okay.
Yes, exam score is 75 percentage.
Okay.
Score out of 100. So 25 marks come from internal mark.
Okay.
Out of 12, 8 will be considered as the best. Best 8 assignments will be considered.
Oh, okay. No, I mean there are still 6 assignments remaining, right, Santya? So I think
Yes, sir.
yeah, that we can do carefully, and yeah, but I mean the keep. I mean, if you find a question that is slightly uh, not if you feel stuck at a certain question, you can mail me as well as there is a forum. You are aware of the forum, right?
Yes, sir. Yes, but I'm not in join in that forum.
Oh yeah, please join the forum. Okay. See, because the advantage is twofold. One is you yourself can ask a question if there is a problem.
Having any link or some other.
No, so you go to that course page, okay?
Yes, sir.
And on the top, there are several links. No, one of those link is called forum, discussion or something like that. Let me check.
Discussion.
Go to the online courses website of the website where the course is. Okay, can you see some? It's called discussion or something like that.
I think you have forum means the Google group only. No?
Google group. That's right.
Okay, sir. Okay.
You've joined that?
Yes, I have no, sir. Now only I have visited the group. Okay, sir.
Okay. Yeah, please join that group and there post the question. Okay. And I mean, you can mail me also, that is fine. But if you post a question there, then firstly, you can get a reply directly from the instructor.
Okay, sir.
Okay. And others may also get help from that. And likewise, if others post it, then you will see the clarifications and you will also get help from looking at the others' questions.
Okay.
And oh yeah, and that is one thing. And also, you can rewatch the lectures, or you can quickly, if you don't want to, rewatch it all through again, you can go through the lecture PDFs, right? It's also uploaded in the course page. You can quickly go through and then check which section is your question about, and then you can review those things, because I think you can agree that uh, I mean, like, at least 60% of the questions come from directly from the lectures.
Okay.
It's yeah, it's about it's just comes from the theorem statements, or something like that. And that is like 60% of the question. Another 20-30% of questions are a little bit more work. Okay, you extrapolate from that, and maybe 10% of the questions are on the level where you need to do a lot of steps and then get to the answer. But please rewatch the lectures, or send me an email, or put it on the forum as soon as you get stuck. Okay.
Okay, sir. Okay, sir. Okay,
Yeah.
sure.
Okay, that is one thing. But I agree that this course is slightly, it has very non-trivial advanced topics. So so naturally assignments will also be difficult. But it's totally fine. So there are 6 more assignments coming up, then you can catch up.
Okay,
Okay.
sir. Okay, sir.
Yeah. Okay. Okay. So before I move on, any other questions related to Kishore Jyotirmay? Okay. Okay. So welcome to week 6 problem solving session. Okay. Again, my name is Bhavya. Okay. I am a PhD scholar from IIT Madras, and so today's topics, I have not prepared a problem set, because the content was very specific to the concepts. So today's will be a slightly conceptual session. Maybe it may be a shorter session, but I thought it was a good time to start discussing the assignments. Okay. So I'll discuss the assignments. The previous assignment question, which was slightly, whose concepts may not be direct. The other questions that I've not discussed, you can get it from the lectures. Okay, I mean, if you see it from the lecture video, but if you still do not find it, then you can let me know. Okay, so this is from assignment week. Assignment week 5. Okay, so here is question number 3. So it says, okay, let P and Q be probability distributions over a sample space of size 20. What is the maximum possible total variational distance? Okay, that's what it says. Now, we had a long session last time in total variation. Yeah, Sanjay, you had something?
Yes, sir. Yes.
Okay. Okay, I know, I thought you were speaking. Okay, sorry. So last time we had a long discussion about total variation distance, right? So what is total variation distance? Okay. Okay, or I'll total variational distance. Okay, total variation distance is a way to measure how like or how different two distributions are. Okay. Given two distributions. Now, what is a distribution? A distribution is a set with, say, m elements, where each element has a certain probability associated with it. Okay, so if you say to sample from a distribution, then if you sample a value x from a distribution, the probability, if you sample from a distribution, then the probability that you draw an element X happens with probability Px, where P is the probability associated with the distribution. Okay. So that is given two distributions, D1 and D2. Okay. The total variation distance, which is called DTV, between the two distributions D1 and D2, okay, is equal to half of half of sum of X within the, okay, so D1 and D2 are distributions over the sample space omega. So D1 and D2, the elements inside it belong to the set omega. Then X in omega, absolute value of D1x plus D2x or minus D2x. Okay. I had given an example last time. Maybe we can see here. So, for example, this one. Here is an example of computing the total variation distribution. Okay. Here, what do I have? Here I have X, which is, so let me assume that the first element is, so the sample spaces say 0 and 1. Okay, sample spaces 0, 1. Okay, it could be bigger, but in this case, it's 0 and 1. And so X is 0.2, X is 0 with probability 0.2 and 1 with probability 0.8. Similarly, Y is 0 with probability 0.3 and 1 with probability 0.7. Okay, so like I said, the formula is half of sum of, okay, each of the corresponding entries, each of the corresponding probabilities. For the first one, that is 0, 0.2 minus 0.3 plus 0.8 minus 0.7. Okay, now this is the example that I discussed last time. Okay, so why don't I copy it in the other notebook? Okay. Okay. So this is what you have, and then we get 0.1, 0.1, and 0.2 divided by 2, which is 0.1. Okay. Now the question is, let P and Q be two probability distributions over sample space of size 20. Okay. P, Q are distributions okay, over a sample space omega such that size of omega is 20. Okay. Now they are asking, what is the maximum total variation distance between P and Q? So dTV is half of sum of X within the sample space and D1 of X absolute value, D1 of X minus D2 of X. So this is the variation. So the sample space is of size 20. Now, forget about this question first. Look at this example. Okay, look at this example. Look at this example, and you can already see that corresponding entries are there. You sum these up, and you sum these up, right? And so, what is the maximum value of this that you can make? So tell me one thing. If you add 0.2 and 0.8, what do you get? You get 1. You add 0.3 and 0.7, you get 1, right? Because it's a distribution and the total probability should always be equal to 1, right? So this 0.2 plus 0.8 is equal to 1. Now if you add this up, 0.3 plus 0.7 is equal to 1. It will always be at most 1. Now, what are you doing? You are adding these two up here, right? 0.2 minus 0.3. Sorry, you are subtracting them. And here also you are doing 0.8 minus 0.7. So look at each of these summands, okay? What is the maximum value that this can get? Can you tell me, like, what is the maximum value that, I mean, okay, here it's of course 0.1, 0.2 minus 0.3. But let me now ask, okay, now observe this question, okay? Now, you see that 0.2 minus 0.3 is 0.1. But you can already see that since each of these distributions, okay, should the sum of all its probability should all be at most 1 for this distribution as well as this distribution, okay, each of those entries can also be at most 1, right? So that is clear. So each of these entries can be at most 1, so this can be at most 1. So let me rather write it as this way. I think it's getting confused with all the values. So x equals a, let's say probability p of a, p1 of b. This is the first distribution. Y is p2 of a, p2 of b. Okay, this is the second distribution. Now, p1 of a, because p1 a and p1 b are probabilities associated with a and b in distribution x, p1 of b is at most 1. This implies that p1a is also at most 1 and p1b is also at most 1. Right. Now, what are you doing? And the same for p2. This also is at most 1. Okay, because this is at most 1. Some of them are at most 1. Their sum is at most 1. So now what you are doing is you are adding them up like this. And adding this, what will their maximum sum? What can be their maximum sum if p1a is each of these elements are at most 1?
0.5, each 0.5.
So 0.5. Yeah, what do you say?
See, P1 of A should be max of 0.5, not more than that, because when we add it, so it should be less than or equal to 1. So that's the reason the maximum value P1 of A can take is 0.5.
Why p1 of a could also take 1, right?
Yeah, but P1 of A, if we take P1 of A and P1 of B, 1 plus 1, it is more than 1, right? The first equation, P1 of A plus P1 of B less than or equal to, it's deviating.
But yeah, okay. Additionally, I have to say something also. But this, you see, P1 of A is at most 1, P1 of B is at most 1. No.
Okay.
And
this equation satisfies. Yeah. But if we take, based on these equations, P1 of A less than or equal to 1 and P1 of B less than or equal to 1, if we take this way, so if we add it, right, so it is deviating the condition.
It is...
so the first equation you have written, right? P1 of A plus P1 of B is
less than or equal to... I made a mistake. Sorry. We should be subtracting. No? You're doing a subtraction. Okay. Now is it right?
Yeah. Then
okay.
Then the max it can go is one is the max, but
this is 1. That's correct. This is at most 1. Because for that to happen, this should become 1. I mean, let's say one of them is 1 and the other is 0. That is when this is maximized. No, it cannot
But
be
still
more
we have
than.
a scope, right? 1 minus 1, 0. So but still we have a scope to increase the value, right?
No, no.
So
If you do 1 minus 1, let's say P2 of A is 1 again. So 1 minus 1 is 0. So that is not the maximum value you can achieve, because clearly if the first one was
let's say
1 and the
then
second was
P1
0,
of A
then
can be 2, right? P1 of A can be 2 and P2 of A can be 1. So
P1 of
1
A, how can it
minus.
be 2? Because P1 is a probability.
Okay, okay. So it's the first condition. Okay.
Yeah. Okay. Yeah, this condition. So this is at most 1. That is fine, right? So now, what about this second one? This part. What is the maximum value when you subtract it? P1 of A minus P2 of B. What is the maximum value that you can obtain?
Same again, 1 I can say.
Yeah. When will you attain 1? Uh, you will attain 1 when, okay, so let's say this is 1, this is 0, then this is 0, this is 1, then you will attain 1. No? I mean, but we are doing absolute value. Okay, so this will be minus 1 technically, but since I'm talking about this formula, so we are talking about absolute value. Absolute value of P1 of B minus P2 of B is 0 minus 1, which is at most 1. And it is also satisfying this condition that P1A plus P1B is at most 1. And P2A, which is 0, plus P2B is at most 1. No? Oh, okay. I think Kishore has some internet connection. Yeah. So, yeah, Kishore, did you hear that?
Oh, sorry. I lost my connection.
Oh, yeah. I thought so. Yeah. Um, so P1B minus P2B is maximized when that is at most 1 when P1B is 0 and P2B is 1. So because it's also satisfying that 1 plus 0, that is P1A plus P1B, is at most 1. This is the first distribution. Sum of first distribution is at most 1. Sum of second distribution is also at most 1. This is 0, this is 1. So you can see that the maximum value this can attain is at most 1, and the maximum value this can attain is at most 1. Clear, no? Okay. So now you observe that if you subtract any two corresponding probabilities, since each of them is at most 1, you will always get at most 1. Okay. So um, so um, for any two probabilities P1 P2 P1 minus P2 absolute value is at most 1. But what are we doing here? We are summing them up. No. Now what are we doing here? We take distribution at D1, which is at 1 and 0 and 0 and 1, and then add them up. No. So that's what we are doing. We are finding the total variation distance. So we are adding this, and the maximum value is 1 for each of them. So 1 plus 1 is 2, right? So if I look at that particular condition, x equals 1 0, y equals 0 1, this was the maximum. Then what do? You do dtv of x comma y is absolute value of 1 minus 0 plus absolute value of 0 minus 1, and this is 1 plus 1, which is equal to, oh sorry, it should be half times, which is half times 1 plus 1, which is equal to 1. So in this case, you get that, okay, this is the, if your random variable is what is called a Bernoulli variable, right? Or the distribution is this based on a sample set of size 2, the maximum variation distance, total variation distance, will always be 1. Because in this 2, in order to maximize this term, half of a minus b plus c minus d, this is the kind of term you have, right? To maximize this term, this I need to maximize, right? This I need to maximize, and this also I need to maximize. Then this entire term will get maximized. But what is the maximum value? Maximum is 1. This is also 1. So 1 plus 1 divided by 2, then the total, I get 1. Okay. So it is clear that if my sample space has only 2 elements, for example, here the elements could be 0 and 1. Okay. Heads or tails, whatever. Then the maximum value of total variation distance is at most 1. Now, but what the question says is the sample space is of size 20. So how will my total variation distance change? That is what the question is asking about. So let's say omega is nowhere 0 and 1. Let's say omega is 1, 2, 3, 4, 5, so on till 19, 20. This is the total variation distance. Okay. Now, what is the distribution? So what is the total variation distance? So I am given d1, d2 over this sample. Okay, is d1 of 1 plus minus d2 of 1 plus d1 of 2 plus d2 of 2 plus so on plus d1 of 20 plus d2 of 20. Right. This is what I have. Now, I want to now like before, see the previous example. Similar to the previous example, I want to maximize, in order to maximize dTV, okay, I need to maximize each of these terms. Same thing. So what is the maximum value that each of these terms can get? Okay, so this term is also a difference of 2 probabilities, absolute difference of 2 probabilities. So this term is also at most 1. Okay, and this term, and you can say similarly this term is also at most 1, and the remaining terms, so you can say this term is at most 1, and therefore you can say this is at most the size of omega, which is 20. Because each of them, let's say this achieves 1, this also achieves 1. Okay, sorry, I have put a plus there. Okay, it should be a minus. Okay, but I'll need to, okay, yeah, okay. This should be minus. So you can use the same logic to say, okay, this is at most 1, the first one is at most 1, second one is also at most 1, this is also at most 1. So let's say each of them attains 1 probability. Okay, let's say each of them attains 1, then we are done. Then there are 20 terms, so each of them are 1. Then it's 20 times 1, which is dTV is equal to 20. That's what we'll think. I also forgot one more thing, to put a half out here. Equals half of. Right, that's how I think. But that is slightly flawed, in a sense that it is not wrong to say that, okay, 20 is an upper bound, but 20 is something that is achievable. Is 20 something that is achievable? is it possible that each of these differences, think about it, I'll give you a moment to think about it. Is it possible that I can have a configuration when all of these 20 terms, okay, all of these 20 subtractions is equal to 1? Is it possible? Think about it.
Yeah, possible.
Yeah? You should- Okay.
It's possible.
When is it possible?
So if each term will be like in a decimal, it results in a 0.1 or 0.5. In that case, adding all of those terms may be equal to 1.
Okay,
Probably.
but yeah, okay, it may be possible, but I want an explicit example where it's possible. So, but I'll ask you a question, one more question, follow-up question. Okay, forget about the other terms. Okay, forget about the other terms. When is this equal to 1? Give me an example. What is the value of d1 1 and d2 1?
When d1 is 1 and then d2 is 0,
Okay, good.
or d2 1, d1 is 0 and d2 of 1 is 1.
Okay, good. So let's fix that. Let's say d1 is equal to 1 and d2 is equal to 0. Okay, we fixed that now. Okay, now fix it. Okay, we have fixed it. Now tell me, given this, okay, and forget about the rest of the terms. Okay, now we look at the second term. Given this, tell me when this is maximized. Sorry, not this. This entire thing is maximized. That is when this entire thing is equal to 1.
Again, same concept. Whether first term should be 0, then the second term will be 1,
Okay, great.
and vice versa.
And vice versa. And this is equal to this is equal to 0, and this is equal to 1, right? Now, good. Okay, so but you agree that this is the only type of cases that can happen. I mean, let's say the other terms don't exist. Okay? This is the only type of cases where they are maximized, right? When one is 0, the other is 1, the other is 0, the other is 1, and so on. Right. This is the only case when I can achieve 1 in those. These blocks equal to 1. No.
Right.
Now, okay. Now I'll introduce one more term, and this follows. I am continuing the addition. Okay, I'm continuing the addition, and I do a plus d1 of 1, the d1 of 3 plus d minus d. Sorry, what am I doing? D2 of 3.
I think it's d3 of 1 and d3 of 2.
D1 of 3 minus d2 of 3. No, there are only two distributions, d1 and d2. Now I'm looking at element 3. No, right? So now I've fixed them. Okay, I've fixed this is 1, this is 0, this is 0, this is 1. Okay, now tell me, when can this be maximized? I mean, when is this achieves the maximum value equals 1? I've fixed them, by the way. Fix these two values. So what kind of setting to d1 3, d2 3 will actually give me equal to 1, difference equal to
1? Well, I guess the same concept again. Either first term 0, second term 1.
Okay, but now be careful. Okay, this is equal to 0, this is equal to 1. Now I am saying that the probability of drawing 3 from the distribution is equal to 1. Distribution d2 is equal to 1. Probability of drawing distribution 2 from the distribution 2 is also equal to 1. So in the same distribution, that is distribution 2, probability of drawing 2 is 1 and probability of drawing 3 is also 1. Isn't that a problem?
Sorry, I didn't get that last statement.
So what I said was, here d2 of 2 is equal to 1. No. Yeah, right. This is the case when this
Right.
entire thing is maximized. This block is maximized. In order to maximize this block, I have set this to 0 and set this to 1. What does this mean? This means that in the distribution D2, probability of drawing 3, element 3, is 1, full probability. And what does this mean? This means in that same distribution D2, probability of drawing element 2 is also equal to 1. So in that same distribution, I have two different elements whose probability I draw, I mean the probability of drawing those different elements is 100%. But how can that happen? A distribution
That happens only in uniform distribution, but this is not a uniform.
No, that does not even happen in uniform distribution. Uniform distribution, everyone has equal probability. So
Yeah.
uniform distribution, for example, tossing of a coin. Okay, uniform distribution over, let's say, two variable. For example, tossing of a coin says 0 with probability. How much? Half. And 1 with probability. Half. Is this also a uniform distribution? U2 equals 0 with probability 1 and 1 with probability 1. This is what is happening here. No, this is what is happening here. Two different elements have probability 1. This is not a. This is an invalid statement to make. This says every time I toss a coin, I will definitely get heads as well as tails.
But the same thing is happening with the term D1 as well, right? Distribution D1 of 1 and D2 of 1, and then.
No, but D1 of 1 is 1 and D2 of 1. What did you say? D1 of 1 and D2 of 1. Which ones?
Okay, maybe I think the 1 and 0 has been interchanged between first probability and the second probability.
1 and 0 are being changed between the first
Because
probability.
in the distribution 1 of 1, 1 we have taken the probability,
Yeah.
but for the distribution 2 of 1, it is 0. When we came to the second element, that is different from the distribution of 1 of 2, it is 0. Whereas the distribution 2 of 2, it's 1.
Distribution 2 of 2, this is 1.
Probably based on this sequence, what I guess is probably D1 of 3 might be 1.
Okay.
And then D2 of 3 is 0.
Let's try that. D1 of 3 is 1 and D2 of 3 is 0. This is what you're saying, no?
Right.
But now what is the problem? The problem is that D1 of 1 is 1 and D1 of 3 is also 1. So if you sample from the distribution, the probability of drawing 1 is 1, 100%. Probability of drawing 3 is also 100%. You see the
And
problem?
in that case, then in this case, probably like we should take the decimals which would be not greater than or equal to 1.
Yeah, right. It will not be equal to 1. It will be smaller because you're subtracting.
Yeah.
Okay, I'll come to that, but quickly I'll just say that you guys see that this is invalid. No, it's saying you are drawing. If you are tossing a coin, you are getting both heads and tails.
Right.
So in any distribution, so let's say D1 of 1 plus D2 of 1 plus, these are all, sorry, D1, okay, or I'll just write, yeah, D of 1 plus D of 2 plus D of 3 plus and so on till all of the elements D of n, where size of omega, the sample space is n, is equal to 1. The sum of probabilities in the distribution should be exactly equal to 1. Okay, that's why this is causing a problem. That's why this is causing a problem. So if you have a third distribution, to say that this is maximized when it is equal to 1 will not work, because you've already run out of probabilities. You've set this to equal to 1, you've set this to equal to 1, and now both the distributions are saturated. Now the question is, now you are distributing the probabilities across the elements within it. No. So this approach is, this saying that it is 20 cannot be true. Okay. Oh, okay. Or not yet. Let us try still. Let us try still. Okay. Now what Kishore is saying is, I'm let's say DTV equals DTV of D1 D2 equals half of D1 of 1 minus D1 of 2 1 absolute value plus D1 of 2 plus D2 of 2 plus D3 of D1 of, this is getting confusing, D1 of 3 plus D1 of 3, D2 of 3 plus and so on till D20.
I think in the first term it is D2 of 1, not D1 of 1. First term.
Oh, sorry, yeah, good. D2 of 1. Okay, D1, D2, 20, 20. Okay, now this is what I have, right? Total variation distance. And Kishore is saying something like, okay, if I assign this maximum value to be 1 and maximum value to be 1, then since I have run out of values to actually allocate the other people. Okay, what I'll do is I will set it equal to something like 0.3, no, 0.7, whatever. That's what you're saying, no, Kishore?
Yeah, that's one way. The other way is, what I mean to say is, see, let us suppose what we are facing, the problem is with the third term, that is D1 of 3 plus D2 of 3, right? So D1 of 3 should be 0.6 and then D2 of 3 should be 0.4. Can we take that way? Which is less than or equal to 1.
Okay, let's see. D1 of 3 plus D2 of 3, no? This is equal to, okay, so you said something like 0.6, 0.4, no?
Yeah.
And, okay, sorry, not plus, this is minus. All over I'm putting pluses. Okay, minus. So 0.6, 0.4, 0.6 minus 0.4 equals 0.2. And then what Kishore means to say is that this is 0.2. Maybe I can do 0.2 plus some other term will add up to 0.5 plus 0.7 plus and so on and so forth, and I'll get more than 2, or maybe it will equal to 20 also, who knows. That's what you're saying, no, Kishore?
Yeah.
Yeah. Now why is, okay, now let's see what happens. Okay, let's say that is true. Okay, that when I, okay, there are two ways to think about it, but okay, let's say that happens. Okay, let's say the first subtraction term, this guy equals 0.3, and this guy equals 0.7, and this guy equals, let's say, okay, 0.2, 0.3 plus 0.7 plus 0.2 plus 0.5 plus 0.8 let's say, and this is larger, at least larger than 2. Okay, and so on. Maybe it even reaches greater than 20. That is one possibility. No. Now, question is, what is wrong with this? Why do we expect it not to happen? This is a difference of two probabilities. Okay, d1 of d1 of 1 minus d2 of 1. Now this is d1 of 2 minus d2 of 2, and so on. Now d1 and d2, they may be something like 0.7 minus 0.4. Okay, now the other one, 0.7, it could be something like 0.8 minus 0.1. Okay, now already I'm seeing a problem. The addition of these two is going greater than 1, which I've said before. The addition, okay, where is it? Which I've said before, the addition of values of probabilities within the distribution should be at most 1, which should be actually exactly equal to 1. I'm already encountering a problem. You can see, if one of them I allocate it as 0.7, 0.8. You get it, right? And
Right.
and so on and so forth. You'll have such a problem. When will you not have a problem? When will you not have a problem? When each of these values, when you sum them up, it will give you 1. No. Okay. For example, if this was for example, if this was 0.3, it is not a problem, because the rest of the terms, it is not a problem. Okay, it is not a problem because when you add these two, you get 1. So that is exactly the case that we'll study. Okay, that as I'm using a particular probability, the total pool of probabilities that I can pick from is actually reduced now. Okay. Here I take 0.3. Let's say, sorry, let's say I have this. No. Now, d1, if I assign a value of 0.3 to d1, and d2, let's say I assign a value of 0.2. Okay, that's what I assign. Then the rest of the d1, so from that total amount of probability of 1, I have already taken out 0.3. The remaining 0.7 probability, I should distribute it among other values of d1. So I already have that if say d1 of 1 is equal to 0.3 and d2 of 1 is equal to 0.2, then the remaining d1 d2 plus d3 d1 3 plus d1 4 plus and all the remaining d20 d1 20. Okay, remaining all values should be equal to 1. Should be equal to 1 minus 0.3, which is equal to 0.7. Because if it is more than 0.7, then the total probability of the distribution will actually be more than 1. And similarly, this d2 of 1 equals 0.2, then d1 of d2 of 2 plus d2 of 3 plus and so on till d2 of 20 should be 1 minus 0.2, which is 0.8. No. Right? Okay. So, so what do you have? Well, now I do this. Now I assign, say, values for D12 and D22. Observe that you cannot exceed 0.7. Okay, because if you exceed 0.7, even if you do 0.71, then 0.3 plus 0.71 is greater than 1. So let's say now I assign it a value of 0.1 and D2's value is 0.3. Okay, so what is the probability left? So D1 of 2 is 0.1 and D2 of 2 is 0.3. Then I have that D1 of 3 onwards and D2 of 3 onwards, they are 0.3 and 0.1 are already used up. So 0.4 probability I've used up. The remaining probability should be distributed. 0.6 probability should be distributed across the remaining, and similarly the remaining probability of 0.2 plus 0.3 is 0.5, so 0.5 should be distributed. Right, so far so good. Okay, now observe one thing, that so this concept is clear. Now observe that I need to distribute these values 0.6, 0.5 and so on. Okay, I need to distribute them and observe that the maximum I can distribute to any distribution is, for example, here I could not put 0.7 because it would increase, I mean, it would be more than 1. So, what is the observation that we make? We observe that these can only be small values. And what do I mean by small values? It will be always less than 1. Okay, it cannot be more than 1. And if I subtract values which are less than 1, okay, A is less than 1 and B is less than 1, then A minus B is less than 1. I mean, even absolute value. It cannot exceed 1. You can try with different things. 0.7 minus 0.8. Always the greater term will be picked, and 8 minus 7 will be minus, okay, absolute value, which will be minus 0.1, which is equal to 0.1. Observe this fact. Absolute value will always be upper bounded by 1. No. So even in this case, each of these terms are at most 1. And furthermore, not only are they at most 1, they are at most the remaining probabilities. Okay, so I used 0.3, 0.2 here. Okay, this guy is at most the amount of probability I've already used, which is 0.3. I'm sorry, 1 minus the amount of probability I've already used. So this is at most 1 minus 0.3. Observe that, because of that distribution thing I was talking about. So which means this is at most 0.7. I have been telling you that for some time. And this is what? At most 0.8. And then I distribute the remaining probabilities. And if I assign 0.7 and here 0.8, then it's over. For the other, all the distribution should be set to 0. Let's say I don't do that. I set it to 0.1 and 0.3. So what is D1 of 3 equal to? It is at most 1 minus 0.3 plus 0.1, which is equal to 1 minus 0.4, which is at most 0.6. So this guy is at most 0.6 and this guy is at most what? 0. So 2, 3, 0.5. Because of this distribution property. I've written it in detail here also. So you observe that um, um, you are finally playing around with the value 1 itself. Finally, when you it cannot happen that when you are subtracting this, okay, it cannot happen that their sums is greater than 2. Why? If the sum is greater than 2, it means that somewhere along the line, okay, somewhere along the line, you've included a distribution which takes more than from what is left in the pool, because every time I'm taking from whatever is left in the pool, no, 0.7, 0.6, 0.7 and so on. And if I take these maximum values that I can take from the pool, I will always add up to 1. And if I take more than what is there in the pool, then yes, I have a chance that when I subtract two values, then I exceed 1. But that is also not happening. I cannot exceed 1 from each of these values. Right? I cannot exceed because both of them, A and B, are smaller than 1. So observe this particular fact that both of them are smaller than 1. Whatever the yield will also be small. In fact, it will be smaller than both of these values. If you subtract, then so not both of these, it will be smaller than the maximum value. So 0.3 minus 0.2, the answer will always be smaller than 0.3. 0.1 and 0.3, it will always be smaller than the maximum, which is 0.3. If I subtract 0.6 and 0.5, the value will always be smaller than 0.6. But that means that the maximum value of this guy is at most 0.3. The maximum value of this guy, okay, is at most 0. Maximum, that is 0.3. The maximum value of this guy is at most 0.6. But what do you have? Well, if you add these up, the max you can get is 1 from the first distribution and 1 from the other distribution. So the max you can get is 2. Is that clear? Okay. So therefore, DTV is at most 1. Is at most 2. No, not 2. Half of 2. So which is equal to, and this is your answer. So the entire reason for this half being in DTV is to keep the value between 0 and 1. So it is easier to read that, okay, if the value is 0.6, then it means that if the value is 0.8, it means that, okay, the two distributions are very far apart. If it is 1, then it means that they are very, very far apart. The two distributions look exactly the opposite, and so on. But that's why the answer is 1. Okay. So you can actually observe this, play around with different distributions. Okay. And you'll observe that, okay, fine, the DTV, the maximum variation distance, cannot exceed 1. Because this internal term cannot exceed 2 only, because you are distributing the same probabilities. There's the same probability. It cannot, even if I use fractional probabilities, it will not exceed 2. Okay. Okay. So we know the formula of total variation distance. Can you try this? This was question 4 in the assignment 5. What do you mean by Bernoulli variable? You can only have two values with their associated properties. For example, a coin toss.
So 0.7.
0.7.
Right.
Okay. Others also, please try.
So I have taken 0.1, 1 minus 0.1, and then 0.2, 1 minus 0.2.
That's correct. So x is 1 with probability 0.1, 0 with probability 1 minus 0.1, which is 9, and y is 1 with probability 0.2, 0 with probability 0.8. Now, what is the total variational distance? So dTV of x and y is equal to half of the corresponding. So 0.1 minus 0.2 plus 0.2 minus 0.8, which is equal to half of 0.1 plus half of
No, that is
0.6.
0.1 minus 0.9.
Yeah.
0.1 minus 0.9 in the first term.
Oh, okay. Sorry.
Yes.
Oh, okay. Yeah, thanks. That is 0.2 minus 0.9, which is 0.7.
Sir,
Second term is
0.1 minus 0.9.
Okay. 0.1 minus 0.2, no?
Yes.
And
And after that 0.
Okay. Sorry. Yeah, thank you.
Okay, sir.
0.9
Okay.
minus 0.8. Correct, no? And this will be 0.1, which is it? 0.2 by 2, which is 0.1. No?
Yes, sir.
Okay. So the answer is 0.1.
0.1 it is. So I have interchangeably taken wrong terms.
Oh, okay.
I've used 0.1 minus 0.9 and then 0.2
Oh, okay, okay.
minus.
Yeah, yeah. I did the same error here here. Okay, okay, yeah. Okay, good. But what is the takeaway? Well, these look slightly similar, no? I mean, you are only changing the first probability by 0.1, and that is exactly what this estimates. This value estimates. The fact that my answer is 0.1. The fact that my answer is 0.1, it's very close to 0, means that the distance is not far. That means these two distributions are very close to each other. But if it was the opposite, you can clear up. If it was the opposite, let's say x prime, y prime, let's say y1 happens with 0.9 probability, 0 happens with 0.1 probability. And now let's compare x prime and y. Okay. X prime dTV of x prime comma y is half of 0.9 minus 0.1 plus 0.1 minus 0.8 minus no, sorry, 0.1, that's correct, minus 0.8. Let's compare half of 0.8 plus 0.7 and 1.5, no? 0.5 by 2, which is equal to 0.75. Is correct, no?
So 0.9 minus, you have given y or y dash? Y you have
Oh,
given.
sorry. Point
0.9 minus 0.2.
2.
Yeah.
2. Okay.
0.1 minus
2, no? This is 2.
0.8.
And 0.1 minus 0.8. That is correct, no? So 0.7. 0.7. Is this fine now?
But the answer is 1.5.
No. This is the answer to question is this. That is already done. But I'm just giving.
Okay, sir.
Yeah, I'm saying if the distribution was this x prime. Okay, this is yeah. I think I confused you guys a bit. That is a different addition. Okay, this is already done. The first part is the main question is already done. I'm just saying suppose given. Okay, this is what I was saying 0.7 and compare it with x. Sorry, now I'm comparing it with y. Okay, and you can already see that the distribution looks quite different from each other. And I'm getting the value 0.7, which is quantifying, which is saying that okay, the two distributions are actually very far apart. Okay, it's closer to 1. Okay. Okay, can you try this question? This was question 10 in the previous assignment. Suppose x and y are two discrete random variables and probability that x is equal to y is 0.1, then what is the maximum possible value of dTV of x comma y?
It's 1, right?
Yeah?
1. The maximum value will be 1 anyway.
Maximum, yeah, but possible value, meaning that one is a okay, why 1?
Because
dTV can
DTV
be
always
always at
DTV
most
always
1, but it's like that is a loose upper bound. I want a tight upper bound, something that is achievable.
so considering
For
this
example, in the
given
previous
data,
question, yeah, considering this theta. For example, in the previous question, saying maximum is 20 is also a valid answer. But now the question is 20 actually achievable? We said that it's not achievable. Right. Similarly, here, I agree that, okay, 1 is an upper bound, but I want a tight upper bound. Here it's written what is the maximum possible value.
I think 0.8.
What is it? 0.8.
Yeah, because probability of x is equal to y is equal to 0.1, it says. So the second term would be 0.1 minus 0.1, that is 0.9 for both the distributions.
Huh.
So it's 0.1 minus 0.9 plus 0.1 minus 0.9, which comes to 0.8 plus 0.8, which is 1.6 by 2.
But these, it's not written that these random variables are Bernoulli distribution, Bernoulli variables.
It's
So
discrete random variables.
it's just discrete random variables. So they could be drawing from a bigger sample space. It could be 10 elements, 20 elements.
Oh.
But yeah, I mean, you can generalize the idea for more elements, right? Hmm. I was okay. The solution that I was thinking of was slightly flawed now that I see.
No, as per the previous explanation discussion, right?
No, for
The
this
DTV
question.
variable,
Yeah.
the DTV variable gives at most 2, at most 2, right?
DTV is at most, yeah, half of
Half of at most 2.
at
Rest of
most.
the,
Yeah.
say, how, irrespective of the number of what do you say variables in that distribution, so the final result what we get is at most 2.
Yeah. This is at most two. This inner block.
Yeah. So multiplied with 1 by 2, it will give at most 1, right? The same thing.
Multiplied with, but why are we multiplying?
Because DTV, we are using DTV formula, right?
Yeah, this is DTV.
Right. Half of a sigma of a XY distribution.
Yes, half of summation of x of x minus y of
Right.
x. Absolute value.
So this summation of x of x and y of x will be giving not more than 2, right? It is at most 2.
Santhya,
Am I right?
there is a lot of feedback coming from your side. Yeah, okay. Yeah, could you mute Santhya? There is a loud sound coming. Yeah, okay, thank you. Yeah, Kishore, what are you saying?
See, the summation term will fetch us at most 2.
Summation is at, yeah, this is at most 2.
Yeah. So now the rest of the what we left is with half multiply by 2.
Yeah, correct.
So then it would be at most 1 again, total answer.
The total answer is at most. No. Yeah, this is okay. This is at most one. That is fine. But we need to use this fact, no, that the probability of x equals y is 0.1. Because of this particular value, it may so happen that the DTV cannot be very high. Maybe it is so that one cannot be achieved. You get it, right? What I'm saying?
Yeah, see, as it said, let x be by two different discrete random variables
Okay.
of, okay. So it says only two variables, right?
Only two
Does it?
variables, but the two variables may draw from a bigger distribution. I mean, a big sample space. But okay, let's do a simple case. When let's say they take a sample space from two, that is they are Bernoulli distribution. Then what is the answer?
Bernoulli is 0.8.
If they are Bernoulli distribution, DTV is 0.8.
Yeah, because 0.1 for x, it's 0.1 minus 0.9. And for y
Yeah,
as well, 0.1 minus 0.1 minus 0.9,
0.9. Yeah,
which
okay.
equals to 0.8 plus 0.8.
Okay, fine. 0.1 minus 0.9 plus
Again, same 0.1 minus 0.9.
same thing. Yeah. So this will give you at most 0.8. That's what you're saying, no? Yeah, so you can already see that one cannot be achieved in this case if it's a Bernoulli variable.
Yeah, one cannot be achieved.
Oh, it probability that x is equal to y. That's what they're saying. No. Okay, no. This question has a slight problem actually. What do you mean that probability of x is equal to y? It means that okay, the
That
distribution is such that if I pick an element from x and I pick an element from y, the probability that they are same is 0.1.
okay.
No? So it's not a direct. It requires some thought, right? It's saying that uh, distribution is such that um, there is some non-triviality here. But yeah, like, right now I'll just move on. Okay, I need to think about this.
Is it something, can we interpret this way? See,
Hmm.
let us suppose x is equal to y
Hmm.
is equal to 0.1. What is the rest of the probability? It's 0.9.
Yeah, that is fine.
So for the rest of
But
the
what do
terms,
you?
it is 0.9. Let us suppose in the space, in the what is it, the sample space, we have 10 elements,
Hmm.
and then the 0.1 probability where x is equal to y will be 0.1 probability. But rest of the terms, right? For the 0.9 probability, there will be rest of the terms.
But the problem is the following. Um, so you have your sample space. No, you have your sample space, and now what you are saying is you are picking x and you are picking y at random
Yeah, same.
according to okay, x and y are
Is it
random.
something we have a two sample spaces, x sample space and then y sample space? and then when we pick sample x sample from x space and then y space, the probability will be they are equal
The
is
probability they are
0.1.
same is 0.1. That is another way to see it. I mean, yeah, that is another way to see it. That is, I have x and y along with their probabilities. I sample one element from x, I sample one element from y, then I'll get that they are both same from with a probability of 0.1.
Yeah, let us suppose the top one is 1 to 10 is x sample space, and then suppose y sample space is 1, 11 to 19. So,
No, they draw from the same sample space. Assume that.
okay.
They will not give a question for different sample space. But assume that they are drawing from the same sample space. And okay, so okay, I think it goes something like this. Okay, I'm not totally sure. So the probability of picking x and y such that they are equal is equal to 0.1, which means probability of x, I pick x, okay, I get x, okay. Probability, this is what is happening is probability that I am drawing an element x, okay, and these are independent with each other, so probability of times probability of y is equal to x equals 0.1 when I go across all x in the sample space. No?
What I wanted to say is probability of xy is equal to 0.1 as per the given problem. So why can't we take probability of x not equal to y is 0.9?
That too you can take. You can take is same as saying probability that x is not equal to y is 0.9.
Yeah, 0.9. Then in that case, right? So first we need to what do you say? Evaluate for this 0.9, and then we add that resultant with the 0.1 divided by half.
But why? No. Okay. So see, that was something that I was also thinking. I mean, that was the solution that I was thinking about. That you have this, or maybe it will work. I don't know. This was the solution I had in mind before. So if I have x and y, this is this is the summation half of distribution 1. Okay. Yeah. I think so. This should be the answer because you read the answer this way. That's okay. This d1 minus d2 of 1 plus. Because I think we are thinking in the same way that
we can put it as a summation of x not equal to y plus summation of x
that's
equal
exactly
to y.
exactly that was exactly what I was also thinking previously. And 10. You mean like this, no? And then what you say is you have this now, but now what you're doing is you're looking at if okay I think it was correct only, yeah. So what you're doing is you're looking at this is essentially difference of probabilities when the elements are equal, no? So these probabilities will total to
What I trying to say is, see, summation of probability which is x not equal to y is 0.9, and summation of x equal to y is 0.1. So including both these will get the at most true value, right? Because what all the terms if we
yeah, but see this, the probability that these represent and probabilities that this represent, how do you connect them? That is the question. This is the probability within the distribution, and this is a function that depends on two values. That is, you're comparing two distributions.
okay, these
You
are
get it what I'm saying? So
right.
yeah, how do you translate this? How do you incorporate it inside? No. So that's why. So yeah. But Kishore, I was actually thinking the same before,
Okay.
and you get the answer that way. But that's why I was, when I saw this question just now for the second time, I came to a realization that something non-trivial is happening behind the behind all this. And I think there is a I remember that there is a connection between probability x not equal to y and DTV, which was mentioned in the book, but I cannot find. I need to look for it right now. So anyway, I'll handle it next week. Okay, I'm sorry for the confusion. Okay, at that time it looked
Is
like,
it something?
yeah.
Can we think this way?
Huh.
Let us suppose as we have a 10 in the sample space, we have 10 terms, 10 elements, right?
Uh,
So the summation terms will have also what we have is 10 elements.
yeah, we have 10 elements.
So with these whole 10 elements, can we equate it to probability of x equal to y plus probability of x equal not equal to y? Can we equate both these things?
Yeah, so yeah, I was wondering as whether that something like that could be done. Well, what I was thinking at least was that this is a difference of probabilities uh, when x equals y. Is that true? Well, it's not exactly true. You're subtracting probabilities. What does subtracting probabilities indicate?
No, why I mean to say is, see, whether you subtract it and then you add it to the n number of terms,
Hmm.
whatever you do, when you have the value of those individual items, we'll do that. But what the problem has given is the uh, after reducing, I mean, like the partial result is, let us suppose the probability is 0.1. How many elements we have as per the space? We have 10 elements. Maybe 0.1 term, 0.1 probability will be applicable to 5 of the elements. Let us suppose.
Okay,
So
that's
for
yeah,
the
yeah.
probability of x is equal to y is applicable to only 5 terms of the space. So
Right,
rest 5 terms will be applicable to the probability x not equal to y.
right.
So as a whole, if we as we given the x equal to y probability, the rest of the probability what is left is 0.9, right? Not 0.9.
Yeah. Well, I was.
It's max of 2. It's max less than or 2, right, for these terms. So probably 1.9 we may, I'm thinking. It's my guess, I'm not sure, but
Yeah, yeah. That was exactly what I was also thinking about previously. But
okay. Okay.
Yeah, some things are not clicking. But yeah, okay. Yeah, but I get what you say also. The you're saying that okay, is x equals 1, that case occurs 0. Uh, yeah, if you have 10 elements, then it means that if I draw two elements, the probable yeah, see that is the problem. That is the problem. So your argument is something like if I had 10 elements, then um, there are there is 1 point, right, 0.1 times 10, where x is equal to y.
Right.
But
See,
yeah,
as they
that is
given 0.1, right? It's a least probability. So, just for our understanding, what we can say is out of 10 elements, only one or two elements are x equal to y
yeah. But
elements.
what do you mean by that? Out of 10 elements, only one element is x equals to y. What does that mean?
No, when we pick it right, probably one time at one instance, both x and y distributions are picking the same element one. Let us suppose
Yeah.
element one. So from the second element, I mean second instance to instance 10, I mean epoch we can say in terms of other way. Let maybe if x distribution, if we pick the second time 2, when we try to pick it from the y distribution, then it will be 3. It won't be equal.
But
And
that's
x equal to 4, and then maybe y is equal to 6. That's all.
yeah, but it's not just about the size of the sample space. See, it means that if I pick okay, if I pick if I sample from x and y 10 times, this is what it actually means. If I sample from x and y 10 times, out of uh, uh, if I okay, it could be any sample size. The sample space could be of anything size. If I pick 10 many times, then out of those 10 trials, there should be there'll be exactly uh, one time where x is equal to y, if the process is purely random.
Yeah, as you said, see, as the probability is given 0.1, if it is 10 elements in the space, then it is one element. If you think
No,
more
no,
than
no.
10, that is
That's what I'm
100.
saying. That's what I'm saying. You're thinking in terms of picking one element from the sample space. You're thinking of picking one element from the sample space. Uniform probability wise, it is true that that whatever probability is associated and so on is one element, 1 by 10. I mean, since it's 0.1 times 10, it is one element. But what I'm saying is that is not actually what is happening. You're not picking an element from a distribution of a sample size of 10, because what is x? What is y in that case? Where does x and y fit into this in your narrative? That is what I'm saying. So, what you mean is you have a sample space, you pick an element, and probability of happening that is 1 by 10, that is also fine. And if you want to say something like 1 by 10 times the size of the element, which is one element, okay, fine, that too is fine. But where does x and y fit into this? What is the role of x and y? You get what I'm saying? You sure?
Yeah, I'm getting. So why I'm saying this, what is the analysis is, what I'm thinking is x and y is not the individual probabilities he has given. He has given combined probability.
Yeah, correct.
So
Exactly. That is
so
the problem. Huh.
here we don't need to focus on the calculations of these subtractions and minus of the individual element probabilities.
Okay. Okay.
So x
Yeah,
equal,
but yeah.
so the total element uh, evaluation will be like as per the given problem, it's x equal to y or x not equal to y.
Hmm.
So the both combinedly will come to this equation, that is each element minus from the both distribution to summation.
Hmm.
So when we have, that means two parts we have, that is x equal to y and not equal to y.
Hmm.
So that can be put into like 1 by of the probability of x equal to y plus probability of x not equal to y. 1 by
Uh,
2,
so what you are saying is
1 by 2,
1/2
0.1,
probability of x equals y
yeah,
minus
plus, uh, plus
probability
like
x is not equal to y. Maybe absolute value. Something like this.
I'm bit confused here whether it is should be plus or minus, but this is how we can place. I'm guessing.
Yeah, this could be true. You want a way to. I mean, this. Hmm.
I guess it is. It should be plus in this case,
Should be plus in this case.
right?
Okay. Yeah, okay. Whether this is equivalent to this or not, not sure. If it is equivalent, maybe this will work. Okay,
Yeah.
but yeah, we'll check it out next time. But the problem is clear that since the probability is talking about two quantities at once, so it takes
Right.
two values, whereas the probabilities inside the distribution is just taking a single value. It's talking about a single value. So
Right.
to map it out, it does not directly map. So, but I'll check it out. Sorry for the confusion. I'll check it out and let you guys know next week. Okay. And okay, we have 10 minutes left. Okay. So let me quickly do some. I'll just do a quick recap of this week's topic. Okay. So. So this week's, I'll just do a quick 10-minute recap. Okay. So this week's topic is what is called the Monte Carlo method. Okay. And well, what is Monte Carlo method? Well, you may have heard in statistics something called law of large numbers. Okay. What is the law of large numbers? It says that more samples you pick, okay, the more closer you get to the expected value. So the more value closer to the average you're going to get. Okay. So, and a good example of this is all those bounds, Chernoff bounds, Markov bounds. For example, Markov bound says probability that x is exceeds a is at most expectation of x by a, right? So expectation of x. So as a increases, okay, a increases, this decreases. So probability of that happening is smaller and smaller. It and as a goes closer to the ex, the probability of x is being close to ex, okay, is closer and closer to 1. So even from Markov equality, you can similarly check for Chernoff bounds also, that they are all talking about the law of large numbers. So the question is, since when you randomly picked, you get closer and closer to the expected value, why not do that? Why don't I take large number of samples and then do some analysis and say that, okay, it is closer to the expected value. So make large, take large amount of samples. Okay, take large amount of samples and analyze the uh, analyze the expectation and say that, okay, since you've taken a large number of samples, you will go close to the expectation and say that, oh, expectation is low, so the algorithm runs in small time, less time. Now, this is called the Monte Carlo method. Okay, and don't confuse it with Monte Carlo algorithm. Also, although Monte Carlo algorithm you can apply Monte Carlo method to Monte Carlo algorithm. Okay, but this is strictly used, okay, to find usually optimization problems, maximization problems, counting, etc. Okay, and whereas Monte Carlo algorithms was used to find decision problems, yes or no. Okay, now one application that is talked about in the lecture is what is in doing applying FPRAS, which is fully the scheme. Okay, fully polynomial randomized algorithm scheme. Okay, so what you have is so we know what randomized is, you know what full polynomial is. Okay, fine. You know what an algorithm is, not just randomized algorithm, but okay, now what is fully? Okay, that is one question, and not a randomized algorithm. Approximation. Huh. So this is the key part. Okay, approximation. Now we are talking about approximation algorithm, which means that I am fine with if my algorithm is an optimization algorithm. Let's say I want to find the maximum number of shortest paths. Okay, or I want to find the minimum number of say multiplications needed to multiply a matrix. And there are minimization problems, maximization problems, which are hard in general, but approximation algorithm does it quickly at cost of the quality of the answer. Okay, efficiency at the cost of quality. Okay, of the algorithm. By quality, I mean it may be the answer I give you. Maybe it is not that bad, but it does not always give you the right answer. It will give you something close. If the answer is 10, I'll give you something like 8, 12, but somewhere around that range. Okay. Now, so this is a randomized algorithm. That is clear. Okay. And say input is X. Okay. And algorithm outputs an epsilon delta approximation to V of X. Now V of X can be thought of as the correct algorithm. thought of as the correct algorithm or the function that you are trying to compute. Okay, or your function to be computed. Okay, in time. Okay, this is okay. Outputs in this approximation. Now, what is meant by epsilon delta approximation? It means that if suppose, okay, or I'll just say for all x, the probability that my algorithm on x minus v of x, the absolute value it computes is at most epsilon times the real value. If this is always respected, and if this is happens with probability at least 1 minus delta times, okay, then our algorithm is an epsilon delta approximation algorithm. Okay, but not only this, we want efficiency, right? We want it to be fast, and therefore it should run in polynomial time. Over. Now this is where the fully polynomial comes. Usually when you talk about approximation algorithms, a lot of times you're only talking about in terms of the input size. Here this is not the case. Okay, runs in polynomial time over. Okay, not only am I talking about the time, the output, not output, sorry, input. Usually this is what happens, right? But I also want it to run in polynomial time over 1 by epsilon. Okay, what is epsilon deciding? It is deciding the quality of approximation. Okay, and ln of 1 by delta. Okay, ln of 1 by delta. Now, why do you want to? Now, natural question is, why would you want to actually run in polynomial time over 1 by epsilon and 1 by delta as well? Well, usually what happens is, 99.99% of cases, when you build approximation algorithms, the number of samples you make will increase the quality of approximation. What do you mean by quality of approximation? Which is epsilon here. No, if epsilon is small, okay, if epsilon is small, then you will be able to. If epsilon is small, then you would probably require more and more number of iterations. And if delta is small, okay, it means the probability is higher, so you'll probably require more and more samples. That is one reason. Another reason is this epsilon and delta, if you do not take them to be constant, okay, and if your algorithm is very dynamic, you do not take them to be constant, then you need to account for the amount of storage that you require for them also. Okay, and if your algorithm takes epsilon and delta also as inputs, okay, I want to run my algorithm until I reach a certain value of delta or I reach a certain value of epsilon, then I need to treat them also as inputs. But you can always see that epsilon is very small. Okay, the smaller the epsilon, the better it is. So I'll run it polynomial in 1 by epsilon, which is a large number. Okay, similarly, delta, okay, it requires log of 1 by delta bits to represent, and therefore I'll do log of 1. That is another reason. Third reason, you'll see in a theorem that was done in the in the course. Okay, and with that I'll stop the. It says if x1 to xm are independent, identically distributed random variables, and mu is the expected value if number of samples. Now, what is number of samples? You run that algorithm over and over again. No, number of samples okay. M is at least 3 ln 2 by delta by epsilon square mu, then probability that 1 by m summation xi minus mu is at least epsilon mu is at most delta. Okay, so m samples provide an epsilon delta approximation. If you're, and this is a very important theorem, which so I would like you guys to remember this theorem. Okay, you can see that if the sample complexity, if the number of samples I do, that is, I run my, I take several random samples, okay, and then I run my algorithm over and over again for an m which is greater than this, okay, then I get a better and better approximation, and finally I get an epsilon delta approximation. Okay, now you see that the time, which is the number of samples, depends on epsilon as well as ln of delta. Okay, this is the reason why I want my algorithm to run in polynomial time over these. Okay, so this is another reason. So that's the reason that FPRS not just requires that I run it in time polynomial, but polynomial in terms of input, but also in terms of 1 by epsilon. Okay, because this entire thing is divided by epsilon mu, epsilon square mu. I wanted to run in polynomial time over epsilon and wanted to run in polynomial time over ln of 2 by delta. Okay, because this is there in my sample complexity. Now, final notes. Okay, final notes. Not two sets. DNF counting. Please. I hope you read you watched the lectures on DNF counting. Okay, and FPRS for that, and independent set. Another FPRS was done in the lectures. And if you have doubts, then you can read the Myths and Markov book. Okay, it's well explained out there why these things happen and what the analysis and all that. Okay, okay, we don't have any more time to discuss. I wanted to discuss the DNF counting at least, but it's going to take time. Yeah, okay, but yeah. So I'm sorry for the confusion in that question number 10 of the assignment. Looks like it requires some other kind of approach, but next week I'll explain that. Okay, but if you have any more questions, then you can stay back, else we can leave.
Okay, thank you very much.
Okay, thank you, Kishore. Okay. Sandhya and Jyotirmay.
Sir?
Yeah, Sandhya. Any questions?
Sir, no, sir.
Oh, okay. Sure then. Okay, then we'll leave then. Okay. Good night.
Sir, excuse me.
Yeah.
Sir, one last question. Can you work out me the last two assignment questions, problematic sums alone?
Okay, sure. Okay, assignment 5. Okay, this question I think is a bit Okay, this question I will work it out. I'll even mail it to you if you want.
Or else give me some of the YouTube video reference.
Okay. Wait, let me check assignment. Uh, the previous one, no?
Yeah,
Assignment
previous
4.
one and last assignment. The fourth assignment, I think so. Wait, I will also check it.
Oh, okay.
Fourth assignment. Yeah, fourth assignment. Some of the problematic sums are there for the same random variables that.
Okay. Yeah, no problem. Okay. Um,
I have missed one of your class. I think before 2 weeks. At the time, whether you have solved these sums or not, I don't know.
I did not solve these directly, but
Yes,
I
related
discussed,
sums.
yeah, some related sums I did. For example, this um, coupon collector, birthday paradox, and so on. But bin and
Yeah.
balls I did not get to do. Probably, I mean, bin and balls also has the same, but there are a few things. Okay, geometric and this was
Yes,
done.
pen and ball. On the day you have solved that pen and ball sums with the example of some other. You have given some other example.
Yeah.
But it's you have given after completing this assignment.
Oh no, really? Okay.
Yeah.
Very sorry. Okay. I mean, sure. Okay. No,
Because
I'll.
the
Okay.
assignment 1 and 1, 2, 3, it's continuously in a particular within 2 weeks they have given the assignment last date.
Yeah, that is actually very sad. When is
Yes.
week's? Okay, this week's assignment deadline is
Tomorrow, sir.
um third, not third, fifth. Oh, fifth is what? Today is fourth. Oh, it's tomorrow. Oh no.
Yes.
And that's week 7.
Sir, I have completed 5 assignments.
Hmm.
Yeah, due date is completed. Week 6 assignment is tomorrow is the last date.
Okay, week 7 is 12th. It's too close actually to the.
Yeah.
This is too close. I mean, despite
But
having.
if I ask any doubt, you will be saying that the answer, the question answer will not be given. After completing this date only, you will be giving.
No, I mean,
Yeah.
when did I answer your question? I think that was. Uh,
On that particular exact day, I have asked.
oh, okay. Okay, really sorry. When was that? Okay, for a quick quiz week assignment 4, no? Oh no, okay. So okay, but I remember at, I mean, the second one, I agree that this random walks question that you had asked, which had a problem in the question. Um that was. Um, oh, okay. Okay, I gave at 19th. Yeah, I remember. This week
Yes.
4s I had given on the day of the deadline.
Yes. Week 4 you have given on that particular day,
Hmm.
but my question on 19th you have given.
Yeah. The next one, yeah, it was, I think, a bit tight for me. I'm sorry for that. Yeah.
Yeah.
Yeah, that one I remember. I unfortunately I had given it after
While
the
taking-
due date.
while, while taking class, while you are taking class, so at the time I have referred that. Okay, it's
Yeah.
all already submitted assignment. Okay.
Oh, you cannot submit once again once you submitted once.
Yes, and yes, we can able to submit the assignments until the date complete. Due date is, if the due date is tomorrow,
Due
after
date
that we
is.
can't submit. Up to the date, due date,
Ah.
For example, tomorrow is the last date for submitting the assignment.
Okay.
Until then, we can submit more. How many times? More number of times we can submit. More than once we can
Oh,
submit.
okay. Okay,
More
I
than,
did actually I did not know about that. Okay, yeah.
until the due date, we can submit n number of times.
Okay. So once the due date is here, then you cannot submit it once again.
Yes.
Oh,
And
okay.
within a second, I mean, up to 12 o'clock we can submit. Before 12 o'clock.
Oh,
After 12 o'clock, and the answer will be visible to us. Which one is correct or wrong? That way, the answer will be automatically generated.
okay. So for example, here it's written 19th. So you need to submit by 19th. I
Yes,
mean,
19th, 9th, yeah, 19th, right, 11:59. Before 11:59, we have to submit at night.
oh yeah, 11:59 of 19th. No,
Yes.
yeah, it's not. So you can make changes to your answer until 11:59 only.
Yes, 11:59 we can make changes.
Oh,
Likewise,
yeah.
tomorrow, March 5th, up to 11:58, we can change the assignment answers.
Yeah, right. Yeah.
In assignment 6, I'm having a doubt.
Yeah, so that's what I was saying about assignment
Yeah.
4. The I had messaged you around 3 p.m. or something like that.
Yeah.
So that was before 11:59
Oh.
of that particular day, right?
Okay, sir. In
Yeah.
some questions, they are asked us to. They have given the checkbox to
Huh.
tick that.
Huh.
That type of questions, how to approach that questions?
Okay. For example,
Because the
okay.
options are more or less similar.
Oh, okay. You need to be very careful. Okay. So yeah,
Yeah.
okay. This can be seen from the lectures. Runtime fully scheme is okay. For example, this one. Okay. Okay. This one I just. Okay. Multiple choice. Okay. Are there any? Okay. Here is a
There
multiple
is
choice.
a checkbox. Yes. Like this was the question. The polynomial time of algorithm in the DNF context. In this, we have to know all these options very well. Then
Yeah.
only we can make an answer.
That is true.
Yes,
Sadly.
yes, that makes me in trouble sometimes.
Yeah, and sometimes it's very tricky. I know, and
I don't know how to approach these type of questions to.
I know. For example, this question you need a little bit of backgrounding.
Yes, not only these questions. Most of the out of 10 questions,
Huh. So see,
3 to 4 questions they are in checkbox type questions.
yeah, that's true. That is true. See, what I at least for these questions, I would say, at least for these two questions, I would say that watch that DNF lecture and also read into. Just it need not be a very complicated read. Just read about reductions and NP completeness. Okay, I'll be talking about it in the next week because it's next week's content. Okay.
Sir, kindly give me some how to approach and how to within the short span of time I have to learn and approach attend the assignment. Give
That
me
is
some.
true. Yeah. Okay. So, see, first I will tell you is identify the easy problems and identify the hard problems. Okay.
Yeah.
Once you identify the easy problems, I mean, for example, like question 1, 2, things that can come from the lectures 3,
Mm.
4, and okay. So those are the easy questions. It can be done directly from the. Okay. Then what is a slightly more harder question? For example, question 9. Question 8. What is the number of independent sets of an undirected graph with 10 vertices and 1 edge? So
Yeah.
here you can do a bit of experimentation. Make a undirected graph of 10 vertices and just 1 edge. Think about how it looks like and visualize it. Try to count it.
Okay.
What you need? You
For
need a.
answer, but for that question, answer is 729. I think so.
The answer is
I think so. 729.
729.
Yeah.
10 vertices, 1 edge only. Could be. I mean, Yeah, could be. I don't know the answer right now. Need to calculate it. But yeah, you need a counting argument for this. Now
Which assignment, sir? I think 4 or 5.
this is six. This is six.
Sixth assignment.
Uh,
Oh, okay, wait.
and
No assignment.
what is the number of maximum independent sets? Maximum independent sets of undirected graphs with 10 vertices and 1 edge. Okay. How many maximum independent? Okay. Okay, so
And
this
768.
768. Okay, okay.
But I don't know. I have referred that,
Hmm.
but whether it is right or wrong, I don't know.
Okay, okay. Um, hmm. Okay. There could be more than one ways to solve this question, and uh, you need to do a careful counting argument. You need to actually, if as long as you understand what an independent set is properly,
Yeah.
uh,
No,
if you're
that is
care,
no two vertices are not connected by an edges.
yeah, a set of vertices where
Yes.
no two vertices are connected by edges. So if you take any set of edges, how many? If you have 10 vertices, right?
Hmm.
How many sets? What is the largest? What is the largest? What is the number of sets you can make with on 10 vertices?
Can we 10 number of? I didn't understand. For
Number
10
of
vertices,
number of sets.
hmm.
Right now, forget
For
about
one
independent.
edge, if you want to connect one edges, we need two vertices.
No, forget about the one edge. I'm just saying we are selecting vertices, okay?
Yes.
You are given 10 vertices. How many ways can you make a set of vertices? How many sets over these 10 vertices are there? V1 to V10. One example is V1, V2. Another example is V1, V3. Another example is V4, V5, V6. Okay.
Yeah.
How many of these sets are possible? 2 to the 10.
Yes. Okay.
I can
It's a okay. 2 power n. Okay.
2 power n. No. Now 2 power n.
You are asking possibilities of making the subsets.
Possibilities of making these subsets.
Yeah.
Now a few of these subsets, and now I'm saying it. There is one edge in that entire graph.
Yes.
Let's say that edge is between V1 and V2.
Hmm.
Okay.
Hmm.
If in my set I include both V1 and V2, then that set does not become an independent set. No.
Yeah.
Right.
If we already chosen that, it will not be an
Independent set. Total I have 2 to the 10, out of which some sets have V1 and V2 as V1, V2 both in the set,
Okay.
which is not an independent set.
Okay.
You are understanding what I'm saying?
Hmm.
So what does that mean? You want to count the number of sets which does not include V1, V2.
Not independent.
Okay, you want to count the sets which does not include V1, V2 both. It could just have V1, that is fine. It could just have V2, that is fine. But both V1 and V2, choosing both V1, V2, that is not allowed.
Okay.
So think about that. So think about counting how many are there. Okay, and
Remaining, see, out of 10, the two is independent. Remaining all will be not. I'm asking.
no. See, I have the set of I have 2 to the 10 many subsets.
Yes.
Okay, all of them cannot be independent sets because in my graph there is two vertices who has an edge between them.
Yes. Okay.
Can you get? There is an edge between them.
Yes.
Now I have different sets. Let's say one set is V1, V2. The other set is V2, V3. I have another set which is V4, V5, V6, and so on. But I have a set. V1, V2, V3. This is not an independent set because it includes V1 and V2, and they have an edge between them.
Yes. Okay.
So this is a bad thing for me. So I'll tell you. Okay, I'll give you one last part. Okay, that is now try to interpret it as you can count it combinatorially also, using some combination, permutation, whatever. But you can also think of it in terms of bit strings. You have a string of bits. Okay, being at which has 0, 1, 0, 1, 1, 1, whatever. What I mean to say is that this represents. Okay, what I mean to say is, okay. So you have a bit string that is something 0, 1, 1, 0, 1, 0, 1. Okay, this is a bit string.
Okay.
Okay, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, there are 10 length. N is equal to 10.
Okay.
What does this represent? This represents a subset of 1 to 10. Why does it represent a subset? Being 1, 2, 3. Now I index them. Okay, 5, 6, 7, 8, 9, 10.
19, yes.
If at position 3 I have a 1, if at position I have a 1, it means that it belongs to the set. If I at that position I have a 0, it means it does not belong to the set. So this represents, what does this represent? The subset 3, 5, 7, 9, 10. Clear? Because at those positions it is 1.
Yes.
So any bit string of length 10 you can think of is always a subset of 1 to 10. Okay, for example, all zeros, which means the empty set. All ones means this set, means you take everything from 1 to 10. Okay. Now you have this graph where between V1 and V2 there is an edge.
Yes.
Now what does that mean? How many now I want to count the number of non-independent subsets. Which means I am including both V1 and V2 into my set. The rest can be anything. Star. The rest can be anything. This string represents a non-independent set, right? Because at position 1 and 2, which represents vertex V1 and V2, at position 1 and 2, it has both 1, 1, which means this represents a subset which takes V1 also, V2 also inside it. And this is a non-independent set. Question is, how many bit strings of this form will be there? How many strings can I have? How many? Count it. Okay. It's a simple counting argument. How many of these kind of strings can I have? Which represents how many non-independent sets I have. Say that count is x. Then I just do total number of subsets, which is 2 to the 10 minus x is your answer. Which counts the number of independent sets.
X means x is.
Huh?
X value is it's 2 power 10, okay, minus x. X remains to be.
X is the number of non-independent sets, which is the number of
Independent sets.
No, x is the number of non-independent sets.
Okay, but
the number of independent set is total number of subsets minus the number of non-independent sets. No.
Okay.
Total number of subsets is 2 to the n.
2 power 10.
2 to the 10. Sorry, 2 to the 10.
Yeah.
Now you need to count the number of non-independent set in order to get the number of independent sets.
Okay.
You just subtract it.
Independent set is 2. Here, 2 vertices.
No.
Remaining is
2 of them, but there could be several non-independent sets. No, it's not just. So, see, for example, this is one independent set, the non-independent set. This is another non-independent set. This is another non-independent set.
Okay.
There could be several.
Yes.
What is the property I want? I want V1, V2 always to be included in order to make it a non-independent set.
Oh yes. Okay.
Okay. And now I'm giving you a hint on how to count those sets. How to count the number of non-independent sets? You count the number of bit strings of this form. You count the number of bit strings of form 1 1 0 0 0 0, 1 1 0 0 0 0, 1 1 1 0 0 0 0, 1 0, 1 1 0 0 0 0, 1 1, and so on. So where the V1 and V2 are always taken into my subset, these are your non-independent set.
Okay.
Okay. Now what I'm asking you to do is simply count. This is what I'm calling as X, and my answer is just 2 to the 10, which is total number of subsets, minus those subsets which are not independent.
Which are not independent. Okay.
Okay, that is your answer.
Okay.
So you slowly build this kind of intuitions as you go. And it's not like, see, if this is a new information I'm giving you about strings. No, it can be done without doing this also. You just using observing sets also you can do that. No problem. But I'm just giving you a simpler way to do it. Okay.
Okay.
But yeah, and for these questions, for questions 5, 6, please read a slightly, okay, you don't need a very deep understanding also. Read slightly on reductions and NP completeness.
Reduction?
And NP completeness.
Okay.
Okay.
Okay, I will do it for this lecture material.
Okay, so
whether it is present in lecture material?
It will be present in the week 7's lecture material.
Week 7 lecture? Yeah. But they have given in the assignment as assignment 6.
Yeah, I know. That is actually very...
That's the actually problem for me.
I know. I tried to raise it. I tried to raise it with the instructor also once.
Yes. For week 7, content is uploaded last 2 weeks.
What I'm telling you is, don't read and don't go through week 7 right now because you don't have enough time. Just read a little bit on reductions, NP completeness. Okay.
Okay.
And this. Oh, okay. Question 5 is actually.
This is my problem.
Question 5 actually it's too much for this course, I think. Okay, but still, just let me know. Just mail me if you get stuck. Okay, try it.
Okay, sir. Okay. 7 also. See.
7 what? Question 7.
Is.
Oh, this is there in the. This is there in the assignment. Lectures.
This is there in the same song.
This is there in the lectures. I mean.
Yes. The enough counting is there.
Okay, there. Look at the theorem. Look at the theorem. It is there.
Okay, sir. Okay.
Okay. Here it is written in terms of order notation. There it's given as an exact value.
Okay.
Okay. There you can get the answer from the book also, that Myths and Markov book I told you about. Okay. By the way, what is sample complexity here? It is M, which is the number of times you need to sample. You need to run the algorithm over and over again. But you check out. It's there in the book as well as. Check out theorem 11.2.
Okay.
In the book. Okay. In the Myths and Markov book, probability and computing.
Okay.
Okay. So from there you will get. See, these things will be there. This book.
Okay, sir.
Okay. So this is there in the list. Fine.
Okay, sir. Okay, I will try.
Sure. Please try it. Okay. And mail me. And if you are stuck, then please mail me either early morning tomorrow or because I may not be checking my mail always. Okay. Or today sometime. But yeah, last moment if you mail me, then I will also I may not be seeing.
Whether if you are give me a WhatsApp number or something, I will take snapshot. If you are able to answer.
WhatsApp number, it's we are not supposed to. I mean, we should.
Share the
Yeah,
WhatsApp number, I know, but then
yeah. That is one problem. So
okay,
okay, but
okay. I will mail
but
you.
see,
I will mail.
within a
I
few
will.
hours, I'll check the mail always. That is
Okay, okay, okay. No issues, no issues.
okay.